In our next section, we're going to talk about how multicast routing fits into the service provider network design, and specifically how the service providers can offer this service to their customers in conjunction with Layer 3 MPLS VPN service. Now, for designs where we are doing Layer 2 services over the service provider network, like circuit emulation with either any transport over MPLS or the virtual private LAN services, multicast routing becomes much simpler, because from the customer's point of view, their sites are directly attached at Layer 2. Now, as we know, with the Layer 3 MPLS VPN designs, the customer is peering Layer 3 routing with the service provider, which means that if we wanted to run multicast routing in addition to our normal unicast routing, we're going to have to run some sort of multicast control plane protocols with the service provider. Now, this section is going to assume that you do already have an enterprise-level knowledge of multicast routing, specifically how protocol-independent multicast works in its sparse mode variation, what are the different ways to assign rendezvous points in PIM sparse mode, and then how the join process and how the registration process works for sparse mode. Once we build the core of the multicast technologies, and then we can move on to this point where we're dealing with multicast essentially tunneling over the MPLS Layer 3 VPN service, and how we can build what is known as the multicast distribution tree, or the MDT, in order to service the customer's multicast traffic over the service provider network. Now, as we take a look at the diagram that I have here on the whiteboard, the network here is made up of the service provider core that consists of the provider edge routers of Router 2, XR1, and Router 5 that are going to be servicing the same customer site. So we have multiple, or I should say the same customer, where we have multiple sites for the VRF. In this case, we're going to call it simply VRF A. So we have A site 1, we have A site 2, and we have A site 3. And these sites are, again, Layer 3 MPLS VPN customers, which means that they're going to be running some sort of routing protocol on the customer edge to the provider edge. Now, as we looked at the different variations before, this could be something as simple as doing static routing. They could be running some IGP like OSPF or RIP. They could also be running BGP. But really, regardless of what the design here, the ultimate goal at the end of the day is that we are exchanging our unicast routing information from the service provider edge down to the customer edge and vice versa. Now, once this information gets into the provider network, we know that for Layer 3 MPLS VPNs, we then also, inside the SP network, have our VPN version 4, or possibly maybe VPN version 6, VGP peerings between the provider edge routers in order to exchange the customer routing information over the service provider core. Now, once we look at the final forwarding of the traffic, when a packet is received in from Router 1, let's say that it is destined for Router 8, the data plane packet comes into Router 2, and Router 2 is going to be doing its lookup based on the final IP version 4 or IP version 6 prefix, and is going to try to correlate this with an MPLS label. And as we know, there are two label values that Router 2 specifically needs to use here. It needs to use the VPN label that is going to tell us what is the final destination we are trying to reach, like Router 8 in this case, and it's also going to find what is the transport label, where again the transport label is used to figure out what is the egress provider edge router out of the service provider network. Because as we know, the devices in the service provider core, like routers 3, 4, and 6 in this case, they are running simply LDP plus IGP, or possibly they're running MPLS traffic engineering, but the main point is that they don't know the specific routing information about the customer. They do know how to reach all of the provider edge routers inside their own network, so as long as we can get traffic to the edge, we can then label switch it further beyond that. But the key point of this design is that there is a direct correlation on a one-to-one basis with the IPv4 or the IPv6 unicast prefix destinations and the MPLS labels, which we know is considered our forwarding equivalency class, or our FEC. Now, when we look at this within the scope of multicast, this design becomes a little bit more complex, because we know with multicast routing, this is used for a one-to-many forwarding paradigm, as opposed to unicast, which is on a 1-to-1 basis, or broadcast, which would be 1-to-all, or anycast, which is any-to-any. But the key here is that we have multiple possible destinations at the same time that we could be trying to reach. Now, there's a couple of different design point of views of how you can solve multicast routing over MPLS networks. Some of the newer versions of this design issue is to use what is known as the multi-point label switch paths, or the MLSPs, where you actually are using label switching, but you are potentially sending the packets to multiple destinations or multiple outgoing interfaces at the same time, but you're using regular label switching. For most of this implementation, this is a much newer way to solve the problem, so it's not available in a lot of the code versions, so we're not going to be focusing on that today. What we are going to be talking about instead is kind of a hack on the MPLS process, that when the multicast packets are coming in and being received from the customer edge, essentially what the provider edge router is going to do is encapsulate these packets inside of GRE, a generic routing encapsulation tunnel. So just like a GRE tunnel that we're maybe running IPsec over for encryption, we could run our routing protocols over GRE tunnels, because we know it's essentially a point-to-point tunnel that is used for encapsulating IP back inside IP, or maybe encapsulating IPv6 inside of IP. But the key is that it is an encapsulation-based protocol, so similar to like how MPLS label switching is, where we're taking the original payload and then adding new headers on top of it. Now, the problem with running multicast over GRE is that you run into a scalability issue, that if I were trying to get multicast connectivity between all of my customer sites here, what I would need to do is to either go to the customer edge routers or to the provider edge routers and manually provision GRE tunnels between all of the endpoints. So between router 1 and XR2, I have a GRE tunnel between router 1 and router 9, then between router 9 and XR2. This would then allow me to run multicast from one to any destination potentially in the network. Now, the issue is that when you add this additional layer of GRE, you're complicating the routing design. Because as we know, with the overall design of protocol-independent multicast routing, or PIM, is that it does not exchange its own topology information. So what the main implication of this is that when you receive a multicast packet in on the router, it's going to be correlating the source address that the multicast packet came from, the incoming interface that the packet was received on, and it's going to correlate this against the unicast routing table, essentially doing a reverse lookup, or what we call the reverse path forwarding, or RPF check, to figure out, is this packet valid to come in on this interface? Now, the potential issue that you run into with running multicast routing and tunneling at the same time is now that if router 1 sends a multicast packet down the GRE tunnel towards router 9, when router 9 receives this in, if the reverse path forwarding check does not correlate with the actual GRE tunnel itself, then router 9 is going to drop this packet when it is received inbound. So you can get this design to work by using the manual tunnels, but the problem is you have to do a lot of hacks on the routing process, whether you're doing static multicast routes or you're running a new protocol like multicast BGP, in order to change what the reverse path forwarding check says. Now, in addition to this, from an administration point of view, changing the routing table, you also have issues with just the amount of tunnels that you would need. And if I have potentially 100 sites on my MPLS VPN, then we know we have that full mesh scaling issue where we have n times n-1/2 based on the number of sites. So you technically can use the point-to-point GRE tunnels in order to solve the multicast problem, but there is a newer standardized way to do this that uses GRE tunnels, but it's going to be using GRE tunnels on the provider side, where in this case, instead of having the customer edge router be the device in charge of doing the multicast peering with the other sites, now the peering job now falls to the service provider on the service provider edge. Now, the idea behind this is that for however many sites are servicing that particular customer, where again, let's say we have VPN A in this case, these provider edge routers are somehow going to already know about each other, whether it's based on a full mesh of VPN v4 peerings, or maybe we have some VPN v4 route reflection, but somehow any provider edge router that is servicing VPN A, eventually it's going to know about all of the other PE routers because it's going to know their VPN v4 routes, and it's also going to know any of the transport labels in order to reach them. So essentially, we already know all of the edge routers that are participating in the routing for that particular customer. Now, instead of configuring then the manual tunnels in a full mesh, either manually between the customer edge routers or manually between the provider edge routers, what this solution does is to configure the GRE tunnel as a multi-point or an MGRE tunnel, where essentially we're doing kind of a network address translation, where as the multicast packets come in from the customer edge, the provider edge router is then encapsulating the multicast packet inside of GRE, but the destination address then is going to be a multicast destination. Now, what this is going to imply, since we are not doing a multicast inside of unicast encapsulation, we're essentially doing a multicast inside of multicast encapsulation, it implies that the core of the service provider network also needs to be multicast aware. Where in the vast majority of designs, this would be using sparse mode, and it would be using source-specific multicast, where essentially all the provider edge routers are going to know about each other through BGP. They're going to automatically form these multi-point GRE tunnels with each other, and then we can encapsulate any of the multicast traffic that is coming from the customers. As it comes in from the customer edge to the provider edge, we can then forward it to any of the other provider edge routers that are interested. And this particular design solution is what we consider our multicast distribution trees, or the MDTs. So again, the overall design goal of the MDT is that when the traffic is received in from the customer, we are encapsulating it inside a GRE tunnel that is using a multicast address as the destination. So as long as all of the other provider edge routers that are servicing that particular VPN are joining this group address, then they should be able to receive any multicast traffic regardless of what particular site that it is coming from. Now, in some of the older iOS versions, there was kind of a hack on this MDT process before it was defined as an IETF standard. It's now currently defined in the RFCs that it is now an extension of multi-protocol BGP, that specifically it is the address family for the multicast distribution tree, or the address family IPv4 MDT. And what the address family MDT is used to do is to encode what the loopback address of the provider edge router that is joining the essentially multi-point GRE network, and also what is the multicast address that they are going to be encapsulating the packets towards. Now, in previous code versions before the address family MDT was standardized, this meant that they had to have some other way to encode this information, because there was not an official extension for BGP that was standardized then. So in order to do this, in previous versions, it used a special route distinguisher value as an extended community value of BGP. And the shortcoming of this is that since those attributes inside of BGP, that particular extended community is a non-transitive attribute, it meant that in previous versions, the multicast distribution trees, or the MPLS layer 3 multicast VPN, was only an intra-AS solution. Or in other words, all of your sites on the layer 3 VPN had to be serviced by the same service provider. There was no way to do inter-AS exchange. But in the current versions, with the standardization of the address family IPv4 MDT, there's no problems with this, because it's a standardized multi-protocol BGP extension, where as long as the provider edge routers are activating this address family, they can then exchange the information of what's the loopback address that's going to be the source of the tunnel, and what's the particular multicast destination that we're going to use. Now, when we see the configuration of this, the actual commands to use are fairly straightforward, but as with any multicast configuration, the issue is typically with the verification. We need to know from a design point of view, what are the potential problems we could run into with the multicast network, and then once the configuration is actually there, how do we test the individual pieces step by step to make sure that the overall design is going to work. So the first thing that we're going to do is start in the core of the service provider network and build the intra-AS multicast, just to make sure that the core is multicast aware, because without this in the core, we're not going to be able to establish those multi-point GRE tunnels. Because again, those destinations are going to be multicast addresses themselves, which means that we have to have protocol independent multicast running in the service provider core. So next, let's take a look at the command line, and again, what we're going to do is build the multicast in the core. We'll then look at the multicast routing on the edge and how we enable the VRF aware PIM process. Because like any other feature in Layer 3 VPN, we have to distinguish between whether we're running this in the global routing table or whether we're running it in the virtual routing and forwarding instance that is specific to that individual customer. So this means that when we look at the provider edge, which again in this case is routers 2, 5, and XR1, they're essentially going to be running two unrelated multicast routing processes. One is going to be for the global routing table, one is going to be for the specific VRF table. And this means that any other control plane considerations, like the rendezvous point assignment for sparse mode, that's going to happen once in the global table for the service provider core, and then again in the VRF table that is specific to that individual customer. So first, let's look at this in the core. We'll build the basics of multicast. Then once that's done, we'll go down to the edges, make sure that's working with the customer, and then finally the last step is going to be to do the address family MDT, again for the multicast distribution tree, to exchange between the provider edge routers that they actually want to participate in the same Layer 3 multicast VPN.